Saxon Algebra 1, Lesson 39. We have a three-parter, although the first two parts really go together to make one part. And it's all algebra, no geometry. The first thing I want to talk about has a super scary name, trichotomy axiom. Doesn't that sound really, really hard and complicated and like, what? Just wait. The trichotomy axiom, tri means three, means that exactly one of these things is true. Either A is greater than B. A and B are just two random numbers, anything you might want to choose. Either one is bigger than the other, the first one is smaller than the second, or they're equal. That's not very sophisticated, is it? That's pretty simple. Compare two numbers. Either the first one's bigger, the first one's smaller, or they're equal to each other. Yes, that's all there is to this trichotomy axiom. Now, why do we care? Why are we stating such an obvious, ridiculous thing? Well, I'll show you. It has to do with our next topic, which are called negated inequalities. Again, a very scary sounding name, but a very simple idea. Let's look at the first example. It says, draw a number line and graph the solution of, it looks like x is less than 2, but there's a line that goes through the less than sign. This is called a negated inequality. You know how sometimes when there's like a no parking sign is a good example of it. They'll have a P and then they put a circle around it and slash it out. That's like what this is. It's like the Ghostbusters sound, right? There's a little picture of a ghost and then there's the circle and the red slash. It means no, not that, right? That's exactly what this line means. So this is saying x, the way we read it is x is not less than 2. Okay, well, if it's not less than 2, that's good to know. But then what is it? Well, the trichotomy axiom helps us understand. If it's not less than, then x must be greater than, or it could be equal to. So when we have a negated equality, we want to use the trichotomy axiom to say, okay, well, if it's not this, then it must be the other one or two pieces. In this case, there were two other pieces, right? Because we said it's only not this one. You'll see sometimes it's a little bit different. Okay, so now we graph it, which is the same as what we've been doing. All we need is to write the 2. We know that we want to include 2 in the solution because of that equal sign. And then it's everything that's greater than. That's our solution. Oopsie. Drew a line through my 2. That's correct. Now, example 39.2 is the opposite of this one. This one starts with the number line, and we have to write the inequality, and then we have to write the negated inequality, okay? In this one, our first step was to rewrite as an inequality. Okay, that's what we do whenever we see negated inequalities, is we rewrite them. Okay, if you're not that, then what are you? Okay, so this other one is slightly different. It's just going backwards through our brains. The picture looks like this. It's got a lot more numbers on it. I'm just going to start at 3, but there's a circle at 3, and it goes this way. Now, the first thing we want to do is write just a regular inequality about this. Okay, so we can see that it's less than, x is less than 3, and then the other question is, should we include 3 in the solution by putting an equal sign there? The circle tells us, no, don't do it. We don't want to include 3, otherwise we would have colored that in. But as it is, John has very clearly indicated an open circle. The picture's in the book. You can look, but you can see very clearly it's an open circle, so that means we don't need an equal sign there. Okay, so this is the actual inequality that this number line represents. But what if we wanted to write this as a negated inequality? Okay, so we just look up here again. Well, if x is equal to 3, or I mean less than 3, that means x is not greater than and it's not equal to 3, right? Now I'm representing all three choices. If it's less than, then it's not greater than and it's not equal to. So this is the negated version of this. Okay, so this I would label as the inequality that describes this number line, and this is the negated inequality that also describes that number line. All right, so two ways of looking at those problems. All right, guess what? We're done talking about the trichotomy axiom. We're done talking about negated inequalities. They're kind of fun. Just remember there's three parts, and if it's not that one, then it must be the other two, okay? Or in this case, if it's not those two, it must be the other one. Okay, hopefully that's as clear as mud in your mind. Part C, advanced ratio problems. More tic-tac-toe boards. Remember, John does not use tic-tac-toe boards. That's only because he's missing out on the fun. We know that they're a great time, so we use them. And we're going to add one little wrinkle to them this time that I think makes them even better. The ratio of red marbles to blue marbles is 5 to 7. Okay, that sounds familiar. Here comes the part that's a little different. If there are 156 marbles in the bag, how many marbles are red? Okay, so if we start out, I'm going to play dumb, and we start out just the way we've done our tic-tac-toe boards in the past, then we would say, and I'll write it all in this time, I don't normally do this, red, blue, these are our ratios, and this is the actual number that we have on hand, right? This person is, again, these people that maintain their possessions according to ratios are kind of OCD, like a person who collects marbles but only allows themselves to have marbles. 5 reds for every 7 blues, right? If they get an extra blue, they give it away. And it says there are 156 marbles in the bag. Well, that implies the total, right? But where do we write? We only have room to write the red and the blue. We don't have any place where we're writing the total number of marbles in the bag. So we now are going to add a total line. I'm going to write total. And we know there are 156. That's the actual number of marbles in the bag of our situation. Now, we're supposed to find out how many marbles are red. Okay, so that's the question we want to answer. But we look at the other rows and go, we don't have enough information about either the number of blues or the number of totals to build that pair of fractions that we want in order to solve this, right? You know how we always have 2 rows? Well, here's the missing piece. In the ratio column, if we know the ratio of reds to blues, then we know that the total in the ratio must be 12. We simply add those 2 together, right? If there are 5 reds and 7 blues, then that means there are 12 in kind of the control group, if you will, or the sample group. So all we have to do is add a total row and then add to get this number. And now we've got a lovely pair of numbers. Now this middle row, the information about the blues, that was helpful in order to develop this total number, but now we don't need it anymore. So I just lightly squiggle it out. I can still see it if I need to, But now it makes it easier for my eye to see, okay, there are the numbers that I want to pull for my fractions. So I'm going to do 5 over 12 equals x over 156. Solving the proportion works exactly the same as it has in the past. And so we're going to cross multiply. And again, I'm not going to actually multiply through. 5 times 156 equals 12x, right? And then I'm going to divide by 12 to get my x all by himself, which is how he likes to be. And now I'm going to see if there's anything I can cancel. This cancels. Can I do any canceling here? Well, let's see. I know that 12 times 12 equals 144. I have that one memorized. I know that. 156 is what we're trying to get to, though, and the difference is 12 more. This is 12 times 1. So this tells me that 156 must be 12 times 12 plus 1, 13. Does that make sense? That's a way to do long division in your head that sometimes feels a little more natural. Pick a product that you know, figure out the difference between that and the number you're shooting for, and see if you can make it all turn out to be the factor of something that's the same. All right, so I'm going to chop those out, and I'm going to write 13 there, and I'm going to write x equals, let's see if I can do this in my head. 5 times 10 is 50. 5 times 3 is 15. X equals 65 reds. Guess what? That's right. Okay, so what makes these advanced problems is that we now have to take into consideration the total, and it's easy to find the total in the ratio column. We just add them together. And very often now, John's going to give us this information, the total in the actual group, as the other part of the problem. This was 39.3. Sorry, I didn't write that down. And now we just have one more. The ratio of fish to crabs in the sea cave was 13 to 4. If there were blah blah number of fish and crabs in the sea cave, how many were fish? So again, we're getting information about fish, information about crabs, then we're getting information about fish and crabs together. So that is a good reminder to us that we must need to add. And honestly, from now on, you can just always write a total row. Okay, so our tic-tac-toe board has expanded. We have fish, we have crabs, and then we'll have a total. Sometimes we might even have 3 individual elements and then a total. These can get kind of fancy, but it's okay. You can just adjust your tic-tac-toe board, but from now on, I think it's easier just to always put in a total. This is our ratio, this is our actual. The ratio of fish to crabs was 13 to 4. And as soon as we write that in, we can just automatically generate our total. If there were 119 fish and crabs in the sea cave, 119 is the actual number of both of them. How many were fish? There's the fish row, so I put the X there. In both of these examples, we're using the top row, but it doesn't have to be that way. It can be the second row just as easily. Doesn't matter. All right, we pull our numbers out. 13 over 17 equals x over 119. We cross multiply. 13, I'll use parentheses this time, times 119 equals 17x. We'll divide by 17. Okay, 17 into 13 is not going to go. Both of these numbers are prime. So I know they don't have anything in common that I can reduce. I'm praying that 17 goes into 119. And I don't have any good ideas about what that might be, and I can't think of any, 170, that's 10 times 7. That's kind of far off from there. So here's what my brain's thinking about. What times 7 would give me a 9? And what I immediately think of is 7 times 7 is 49. So maybe this is 17 times 7, because that would give me the 9 there. So I'm going to go over here and I'm going to go 17 times 7. That's my guess based on just looking at that last digit. 7 times 7 is 49. Oops, I wrote down the wrong one number. There's the 9. Carry the 4. 7 times 1 is 7 plus 4 more is 11. Look, there it is. So I can reduce this against this and get a 7. And I can write x equals, and it's 13 times 7. So let's see. 7 times 10 is 70. 21. 70 plus 21 is 91 fish. Let's see if it's right. Guess what? It is! Yay! I just think of Little Mermaid when I do that problem. Flounder, what's the name of that little yellow fish? I don't know. I didn't watch that movie very much. My kids did not like it when they were little because Ursula is too freaking scary. And I agree with them. I was terrorized by Disney movies and did not like them at all when I was growing up. And my daughters did not like them at all when they were growing up. Now that they're a little bit older and a little bit tougher skinned, they're fine. But we have never been into the whole villain aspect of Disney movies. So that's the backstory on my life. Aren't you glad you know? Okay, advanced ratio problems. Moral of the story, always add a total line now, and you just add together these two numbers to get this one. All right, 39 is done. Oh, I want to tell you for your homework, for this lesson, 39, I want you to do all the practice. And let me just look at the homework really fast. I think I want you to do 1 through 15 odds. Yes. I'm just looking for negated inequality problems and making sure you get some. Yes. Problems. The problem set, I want you to do 1 through 15, the odds only, okay? That way you are doing about 8 problems, and that is my Thanksgiving gift to you. All right, thank you, goodbye.